Let's just start with a number, a really big one. 43%. Get this, almost half of all climate-related disasters that happen on our planet are floods. This isn't some distant threat. It's a constant global reality.
So how in the world do you stand up against a rising tide like that? Well, you engineer a defense. And that defense is built on a blueprint. A really complex, absolutely critical, and yeah, often flawed blueprint for survival. Today, we're breaking down the engineering behind it all, flood forecasting.
Okay, so let's get right into it. At its core, what is flood forecasting? Well, it's the science of prediction. It's about taking just a massive amount of data, everything from rainfall and snowmelt to river levels, and turning all that noise into a clear signal. A forecast that tells us not just if a flood will happen, but how big it's going to be, when it will hit, and how long it's going to last.
And the need for this science isn't spread out evenly, not even close. The data reveals a pretty shocking concentration of risk. A staggering 70% of all global flood disasters happen in Asia. That really shows you where the front lines of this battle are. This brings us to the most important question. Why pour so much effort into predicting something so chaotic? Well, it's because the stakes couldn't be higher. This is not some abstract academic exercise. It's a literal race to protect lives, communities, and entire economies from being washed away. So let's break down exactly what we're fighting for here. It really comes down to three big things. The most important, of course, is life safety, giving people enough warning to get out of harm's way. Then there's economic protection, safeguarding critical infrastructure, businesses, and people's homes. And finally, it's all about enabling a coordinated emergency response, so help can get in place before the disaster, not after. Even from a purely financial perspective, the logic here is undeniable. This isn't just a cost, it's one of the best investments a society can possibly make. The numbers show that for every single dollar spent on these warning systems, you see a return of $4 to $10 by avoiding the massive costs of disaster response and recovery. That's a huge payback. But here's the thing, the challenge is getting harder. There are two powerful forces making everything worse. On one side, you have climate change, which is bringing more intense rainfall and rising sea levels. And on the other, you've got rapid urbanization. That means more concrete and asphalt, surfaces that can't absorb water, and more people packed into areas that are really vulnerable. So how do you engineer a solution for a problem that keeps getting bigger and bigger? You have to build a better blueprint. And this blueprint is what we call an early warning system. It's our most sophisticated strategy for trying to manage flood risk.
So let's look at the schematics for a minute. In a perfect world, this system is a seamless four-step process. First, you've got to collect a ton of real-time data from sensors and satellites. Then, you feed all that data into powerful computer models to generate a forecast. After that, you have to translate that forecast into a clear warning for the public. And finally, that warning triggers a coordinated emergency response.
And here's the crucial point. A well-designed system like this completely flips the script. It allows officials and the public to be proactive, to prepare and act ahead of time instead of just reacting to a disaster that's already happening. It's a total game changer. Which leads us to the really hard question. If we have this elegant blueprint, this ideal system on paper, why do we still see catastrophic failures? Why do devastating floods still seem to catch entire communities completely by surprise? Well, the answer is that the blueprint has cracks. In the real world, the system is under pressure, and it tends to fail at three main points. The data we put into the system is often flawed, the communication chain is often broken, and the resources to build and maintain the whole thing are usually scarce. Let's start with that first crack, the data. A forecasting model is only as good as the information it's fed. Garbage in, garbage out. And a lot of times that information is compromised. We have way too few monitoring stations, especially in remote areas. The data we do get can be incomplete, delayed, or just flat out wrong because of poorly maintained sensors. The second big crack is communication. A perfect forecast is completely useless if it doesn't reach the right people in a way they can understand and act on. We see these last-mile gaps in getting warnings to remote villages, a serious lack of coordination between different agencies, and then there's the public, who can get desensitized by false alarms. That leads to warning fatigue, where people just stop listening.
And there's a fundamental scientific challenge here too, and that's uncertainty. Every single forecast has a margin of error. That's because the models have to simplify incredibly complex physics, and the weather itself is just, inherently unpredictable. So forecasting is a science of probabilities, not certainties, and trying to communicate that is incredibly difficult.
And all of this gets even harder because of very real-world hurdles. Financially, these systems are expensive to build and operate. Technically, there's a global shortage of people with the skills to run them. Geographically, predicting water flow in complex mountain terrain is an absolute nightmare. And institutionally, just getting different countries to share water data across their borders can be a huge political challenge.
But the story doesn't end there with the problems. No way! Engineers and scientists are actively working to reinforce this blueprint, patching up those cracks with a whole arsenal of modern technology.
And you can see how these new tools directly address the old problems. We're using low-cost IoT sensors to fill in those data gaps. We're using cloud computing for the raw horsepower needed for better models. GIS helps create intuitive map-based warnings that people can actually understand. And satellites can finally help bridge that last-mile communication gap to remote areas.
And the payoff for getting this right is just huge. The data is clear. Implementing these effective modern forecasting systems can reduce flood damage by a massive 30 to 50%. That is the tangible, real-world result of building a better blueprint.
However, and this is a really crucial point, technology is not a silver bullet. It helps, for sure, but it doesn't magically solve the core challenges. We still need high-quality data, we still need clear communication, and we still need cooperation between all the different agencies. It's an ongoing battle.
So we're left with this final, urgent question. Our blueprint for survival is without a doubt getting smarter, more sophisticated, and more effective every single year. But as our planet changes at an accelerating rate, bringing more extreme weather faster than ever before, can we build it fast enough?